Okay, class. Today we are going to have a look on the sway frame example. Okay, the examples are provided to you. Some of the sections has been filled with answer. Okay, then we are going to go through together how these solutions has been done, and some of the parts, okay, that I have actually put it an empty. Then we are going to work on it. Okay, in this practical, or I would say tutorial session. Okay, a combination of a briefing and the tutorial session, and of course some of the parts maybe we are going to put a detailed calculation as well. Okay, so make sure you have prepared your exercise book, your all the existing stationery. Okay, so we're going to go through this the whole example or the questions for a sway frame. Okay, so of course I will get help from your class. Okay, helpers will be called, and you need to help me in some of the solution. Okay. Okay, so let us start. I will switch to the PowerPoint slide. Okay, so that this will be, I would say, maybe a more clearer or bigger picture for you. Okay, so now let us have a look on this problem. Okay, this is a sway frame. Okay, why I say it's a sway frame? Because there is a horizontal force acting horizontally, and this will make the frame sway. Okay, so there are more criteria, okay, that will confirm the frame either it is a non-sway frame or sway frame. Okay, so please visit the criteria, okay, in my previous lesson. Okay, but we can give a reason to why this frame sway is because of this 30 kilonewton horizontal force. If this 30 kilonewton horizontal force is removed, means that not exists in this problem, this frame is non-sway frame, because if you can see that this is symmetrical in terms of loading and also the geometry, and we have a same support condition and same EI. EI is constant. Okay, so let's have a look on how to solve it. So this is a concept of solving a sway frame. Okay, so if you can see that this is the actual structure. Okay, so the actual structure, we have 30 kilonewton at B, we have 100 kilonewton per meter UDL on BC. Okay, so this is the deflected shape, okay, of the sway frame. It's going to deflect, okay, with the direction of this horizontal load. So we are going to carry out this analysis by method of superposition. There will be stage 1 and stage 2 analysis. Stage 1 will be dealing with non-sway analysis. How we do that? We are going to apply a restraint, artificial, imaginary restraints here. Means that we will stop the sway action, okay, of the frame. When this restraint has been parked at the appropriate place, okay, so you will have a reactions, okay, generated from this support. A restraint. Okay, so we have this R that we need to determine later. Okay, so here the loading 100 kilonewton per meter, 30 kilonewton, the real loading is still applied in this stage 1. So with this loading, we can determine the fixed end moment. Okay, and this fixed end moment we can put in the moment distribution table. Okay, and the analysis is just conducted by exactly like the beam analysis or non-sway frame analysis. Okay, then we move to stage 2. Okay, as you know that we are using a method of superpositions. So this in stage 1, this R is not exist. This is imaginary. So in the real case, there is no R. So to achieve this equilibrium or to cancel out this R, we need to apply another R we call R prime that acts oppositely. Okay, so then R plus R prime, it should be equal to 0. Okay, but we are not talking about the value of R and R prime here because they are all in imaginary, and we have made assumptions on that. Okay, so in your calculation later, the R value and R prime value will not be the same. Okay, but the direction must be opposite. Okay, be careful. So stage 2 sway analysis, there is no loading, okay, on this frame except the R prime. Okay, then you might ask how to determine the fixed moment, because if you don't have fixed moment, how to distribute the moments, okay, in the moment distribution table. So now this R prime will cause this frame to sway. Okay, when there is sway, there will be deflection happen, okay, in the members. Okay, so this deflection will cause fixed end moment. Okay, so in this class today, we are going to have a look on how to determine, okay, the fixed end moment due to deflection. Okay, so once you have get to know on this concept, okay, we are going to start, and we're going to start with the stage 1 non-sway analysis. So because we need to put in the moment distribution table, we need to determine the distribution factor. So before we need to determine the distribution factor, we need to determine the member stiffness factor. Okay, so maybe class, I will open freely right now. Okay, can you tell this joint A, B, C, D, what is the condition? Okay, either it is a fixed condition or it is a pin condition. So let us start with A, class. Do you think this A is pin or fixed condition?
Fixed condition.
Fixed.
Fixed.
How about B and C?
Fixed condition.
Fixed. Yeah, because this is internal, so it will be fixed. Okay, how about D?
Fixed condition.
Yeah, so all of these are fixed. Okay, but sometimes you will find here has an internal hinge here. Let's say BC near to C. Okay, so then C at this particular BC at the end of CB, you need to consider as pin. Okay, so if there is an internal hinge, but not in this case. So I think you can guess what is the equations to be used for member stiffness factor. We have two. One is 3 EI over L and the other is 4 EI over L. So class, what do you think?
4 EI.
Yeah, very right. So 4 EI over L. So I would like to remind all that this L is the length of the member, not the 4 meter. Huh? It will be the length of AB. So it will be 5. And this BC will be, length will be 4. And CD will be 5. So this is a symmetrical in terms of geometry. Okay. So after you have determined the member stiffness factor, we can put it in the distribution factor. Okay. So here I just put it in the table. You can put it in the equations. Okay. I will quickly show revisions. Okay, how to get, let's say, for BA. So remember, before we come to that, we need to know that DF for fixed is 0. Okay, DF for pin is 1. So without any calculation, you can just put your value. Okay, so for A and D, we have solved it. So for DFBA, okay, the equation is, because we are talking about here, BA. Okay, it is close to B, right? And it is for member BA. So you're talking about KBA, okay, which is 4 EI over 5. Okay, divide by KB. When KB means that there are two members that joining at KB, at joint B. So it will be KBA plus KBC. So that is why here you have divide by KBA plus KBC. Okay, means that is 4EI over 5 plus 4EI over 4. Okay, then you will get the 0.444. Okay, so we're not going to get details on this, okay, distribution factor, but this distribution factor are going to apply for both stage 1 and stage 2 analysis. Okay, make sure you get it correctly. Okay, so then for the stage 1, we're going to get this moment, fix a moment. Do I give you an answer? Let me see. Yeah, I've give you an answer there. Okay, so let's see how the answers being calculated. Okay, so you need to identify fixed moment if there is any loading on the member. So if you see AB, there is no loading. BC, yes, there is 100 kilonewton per meter. CD, there is no loading. So only member BC. Okay, you find appropriate case. Okay, from your appendix. Okay, get the right equations. Okay, WL squared over 12, and be careful on the direction. So remember, counterclockwise is negative. Clockwise is positive. So then you just need to apply. Look at the template. W will be the loading. So W will be 100 here. And the length will be 4 meter. Okay, so can you check whether you get an 133? I give you a minute, okay, to understand this fixed moment. Okay, so class, what do you get for this fixed moment BC?
133.
133. Is there
Yes.
any point form at the back?
0.33.
0.33, yeah. So this is how you get your initial moments or fixed moment. Okay. So you need to are very familiar with the method so that you can act fast. So now you have done with the fixed moment, we can go to the moment distribution table, right? Put in all the join, put in all the end of the member, and okay, put in the DF, okay, and the fixed moment. If you realize that the fixed moment happening only at BC and CB, so you must put it correctly, okay, at the right position. So maybe we're going to look a revision back, okay, how to get the 59.24, okay. Okay, maybe we can call helpers to explain on this, okay. How about Nurin, Akila? Are you here?
Yes, madam.
Yeah, can you explain 59.25, how we get this value at the balance and distribute step?
Negative 133.33 plus 0 times negative 1, then times with DF 0.444.
Thank you very much. Okay, so Nurin is telling that you need to put in the summation of all the moment at the joint B, which is negative 133.33 plus 0, and then multiply with negative 1, which we balance it, and we distribute by multiplying with the DF. Then we get this value. Okay, so I suppose the remaining values, yeah, please try later after the sessions. Okay, then I would like to call our helpers to talk about the carryover. Okay, explain on the carryover. So how about Farzana, are you here? Nurin Farzana? Nurin Farzana, are you here?
Yes, doctor.
Yes. Can you explain on the carryover? So why this arrow is in such?
Because of the arrow of the uh, element.
Yes, this arrow means they are carried over to way actually. To the fixed end, right?
Yes, doctor.
Yes, because we are considering A join A, B, C, D also the fixed end. So from there will be a moment's carry over from AB to BA and BA to AB. Okay, ends. So can you tell me what is the answer for AB at the carryover stage here? How to get this value?
Half the value.
Yes, you are right. Okay, so we get the we will carry over the value at the row before. Okay, this moment and follow this arrow. Okay, half of it divide by 2 or multiply 0.5 to get this. Okay, thank you very much. Okay, so then you're going to continue all these steps until you get very close. At the balance and distribute very close, okay, to 0 here, or very small value. Then you stop it, and then you sum up all the moments starting from fixed moment. Okay, then you will get the final moment at stage 1. This final moment we give a name M1 here. Okay, so we are going to use it later. All right. Okay. So I think this is new and we are going to do this together. Okay, so let me see your PDF file. Okay. All right. Okay. So I would like all, okay, to sketch in your exercise book, okay, the free body diagram. Okay, so if you can see that this 200 is not there yet. Okay, yeah, please draw it. Probably we can do it together. Shall I keep? Maybe I will just copy the whole page. Oops, it's difficult. It is difficult. Let me see. Bit. Okay, so in your exercise book, okay, try to draw a free body diagram for all the members. Okay, of course, I'm going to do this here as well. Okay, if you do not know how to start it, okay, yeah, you can have a look here. Okay, so we are going to split all these member. So they will be member AB. Okay, they will be member BC. There will be member CD. Oops, not straight. Okay, then put in all the fixed end reaction. Okay, at the all the ends. Okay, so we have AY, we have AX, okay, we have MA. Let me follow the, oops, too much. It's at the back. Okay, I want to know the direction because I calculated. Okay, so and the MA. Okay, so these three reaction, okay, either translation in X, in Y, and in moments, rotational. So you need to put in all the joints here. Okay, can you do it now? So this would be BY. Okay, we have BX, and we have MB, but I do not know what is the. So yeah, the MA, MB, we will put it later because we already know the answer actually. So we have BY. Okay, we have 100 kilonewton per meter. We have the other 30 kilonewton. We have BX. Okay, we have CY. We have CX. We have CY. We have CX. Make sure when you write this CY, okay, it will be opposite in the other C. Okay, this is upward and the other will be downward. Okay, so that you will achieve this equilibrium. And both this CY must have the same answer. Okay, then we have DY. Okay, we have DX. Okay, and then we have MD. So now I would like to put in the M. Okay, this M, A, B, C, D, we can take it from the table. Okay, so the table M1. Okay, let me open it here. This one. Okay, this is a moment distribution table for M1. If you can see that, we need this value. I'm going to print screen this one to take it in the page. Okay. Okay, so if you can see that, okay, if you can see that, the first M1 is 41.01, okay, which is positive, means that we are going to draw it clockwise. So MAB here, okay, we already know the value, which is 41.01, and which is, it should be acting at the clockwise. And we move to BA. BA is here, MBA, and it is also positive, so means that clockwise. So here I have MBA. Okay, and I know that it is 82.04. Okay, then I continue with this. Okay, BC. BC is here, MBC. Okay, negative means counterclockwise. So I have this, which is MBC. Okay, 82.04. Then I continue with this 82.04 clockwise, okay, which is MCB, okay, 82.04. Then I continue with CD, which is negative, okay, counterclockwise, okay, which is here. So I have MCD 82.04. So don't put negative 82.04 here because you already put in the direction counterclockwise. Okay, but if you put it clockwise, then you need to put it negative. Okay, so then for DC, it will be counterclockwise as well. Okay, which is in this way. So it will be MDC equal to 41.01. Are you clear, class? Now I have put in all the, draw the free body diagram.
Clear, doctor.
Clear, doctor.
Okay, so probably I will give you a minute or two to draw your free body diagram and understand that. Okay, and we will continue to solving these reactions after these 2 minutes. Okay. Okay, class, raise your hand if you are not ready yet. Okay, so let us continue with solving the reactions. Okay, if you can see that I have put a tips here. Okay, so we are going to follow these tips. If you found, if you compare to the lesson that I share with you, I mean for the class 1, okay, so you will find that this example or this problem has extra steps. Okay, so let's see, okay, how we tackle with this. Okay, so I'm going to read this. Okay, you might take these tips as well. Okay, so in order to determine the R, we need to use the summation fx equal to 0 for overall structure. Why? Because this R is in horizontal. If the R is in vertical, where the frame sway in vertically, okay, then you need to take summation Fy equal to 0. Okay, but if you look at the overall system here, we don't talk about the free body diagram for the internal one. We talk about the overall. Okay, so it will be the overall. I think I better draw it quickly here. Okay, if I talk about overall, it will be something like this. Okay, talking about Fx only, so we have 30 kilonewton, we have R, and we have Ax, and we have Dx. Talking about Fx only, so missing inputs are Ax and Dx. So we need to determine Ax and Dx first before we can solve for the R. Okay, so these are the strategy now to obtain the Ax and Dx. Okay, so we are going to start with the section BC. This section BC. Okay, so in order to solve for this BC, we need to solve for the BY. If you can see that, the previous one we have plot. Okay, so BC, BY is unknown, CY is unknown. Okay, so we can solve BY or CY by just taking summation moment at the other end. So if you want to find BY, you take summation MC equal to 0. Okay, so let us try it. Okay, so meaning that right now BY is unknown yet. Okay, this 200 is the answer for the BY. Let us see how to get the BY. Okay, I would like to ask the helpers here to solve for this BY. Okay, so can I have Noor Nafisa, are you here? Okay, so do you know how to get BY? We take summation MC equal to 0. Let us try, just try. Okay, so let us try looking at member or section BC. Okay, we take summation MC equal to 0. Okay, can you write the equations? Okay, so maybe let me help you. Okay, there is a loading will be contributed to the moment will be the 100 kilonewton per meter and BY. But now the BY, we don't have the answer yet. Okay, we are going to find whether the BY is 200. Are you okay?
Yeah.
Okay, can we start with 100 kilonewton per meter? Just now, my helpers?
Yeah. 100
Yes.
times 4.
Oh, correct. I forget to give you the length, 4 meter. And then the distance to C?
2.
2, correct. Okay, positive or negative for this?
Positive.
Positive? You'll be negative, right? Excuse me. So because we assume clockwise is positive, right? But this 100 kilonewton per meter is acting to C is counterclockwise. So we have a negative 100 times 4 times 2. Then how about by? Is plus or minus?
Plus by.
Yeah, plus by multiply.
Equal to 0.
Sorry, the distance is?
Oh.
4.
4.
Yes, so equal to 0, right?
Yes.
So what is your by? What do you get for your by?
200.
Yeah, thank you very much. I would like you to help also the next. Wait. So you have find the by. Okay, so what you need to do is you are going to continue to bring this by. Okay, comes to the other sections AB. So this will be 200 as well, right? Because the by must be in equilibrium. So by acting at the BC section and by acting at the BS section must be 200, the same value, but opposite direction. Okay, so once you know that this by is 200, if you analyze the AB, what is the AY? Now AY is also unknown at this moment. Will it be also 200, class?
Yes.
Yes, because you get summation Fy equal to 0, you will solve for the AY because there is no other vertical loads here. Okay, so AY is 200 kilonewton acting oppositely with this BY. Okay, so now once you have already solved for the AY, okay, this is number B. We solve for, actually we want to solve for AY. Why we want to solve for the AY? Is because our final aim is to get the AX. Okay, so let us now move to C. So for section AB, once the AY is obtained, AX can be also obtained, okay, by using summation MB equal to 0. Okay, my helpers, please let us try on member AB now to solve for AX. Okay, taking summation MB equal to 0. Okay, can we try to write the equations? Now AX is also unknown, but AY is already known value. Can we start? Oh, I forget to give you a dimension. This is 3 meter, this is 4 meter. Okay. So let's take the AY first.
200.
200. The distance is?
5.
No. 3, correct. So this is acting clockwise, so it is positive. And then next?
Minus.
Minus. AX.
Minus AX.
Yes. The distance?
5.
The distance is 4 meter. Okay. Then, don't miss out the moments.
Minus.
No.
Plus.
Plus.
41.01.
And then, this moment also don't forget about it. Plus.
200.
No, this moment.
82.04.
82.04. Do you have any more contributor? If no, yeah, then you equal to 0. Okay, can you get your AX now?
Uh, 108.05.
Okay, you get this value, right?
Yes.
Okay, thank you very much. So this is how, the strategy to get the AX. Okay, if you remember our previous case, where we have this the typical frame like this. Okay, so we can get this, the AX and DX, just use the, the section for the columns. Okay, we can get it easily, directly, without going through the section BC. But this cannot apply for if your frame has a diagonal member. Okay, so be careful. So there is one more step that we need to analyze for BC first, and then transfer the information from BC, okay, to AB to solve the AX. All right. So to make sure you really understand this, please continue with your free body diagram to solve for your DX. I give you 2 minutes. Okay. So probably you shall refer to this. Okay. So now you already get your BY is 200, and you can get your CY is also 200. Okay, by using the summation FY for member BC. Okay, please continue from here. Okay, to get your DX and check with the answer. Okay, so I give you 2 minutes to try it. Okay, quickly. Okay, please raise your hand if you are not ready. Okay, please raise. Okay, so I will wait for another 2 minutes. Okay, for this. Okay, I think we can continue. Okay, so we are here. Okay, so once you have determined the AX and DX, okay, then we can use this, the summation fx equal to 0, okay, to solve for the R. Okay, if you look at this, okay, conditions here, okay, situations here, you will see that we will apply an equation summation fx equal to 0, where negative R, okay, plus AX minus dx plus 30 equal to 0. By substituting your AX and dx value, you get the R is equal to 30 kilonewton. You get a positive, results here, means that your R directions, what you assume is correct. Okay, so means that they are going to sway towards your right. Okay. So then we can move to stage 2 analysis. Okay, so let's move to the stage number 2. So stage number 2, okay, we no need to determine the DF anymore because the DF from stage 1 can be applied here. Okay, then we can directly go to determine the fixed end moment. Okay, so for fixed end moment, let me see, I have a 2. Where is my appendix? Okay. Okay, I would like to get ready with my appendix first, dealing with the deflection. Okay. Maybe I just save this. All right. So we're going to use this later, this equation, dealing with the deflection. Okay. So, but now let us have a look on this. Okay. Please draw. This shape. This your the sway frame in your exercise book first. Okay. We are going to draw the deflected shape. Okay. Because by drawing a correct deflected shape, only we can determine for the fixed end moment correctly. Okay, so can you do this first? And then please plot, okay, the new position for B and also C. Okay, so 1 minute later, I will tell you where is the position of B prime and C prime for this case. Okay, let me show you where is the B prime and C prime here. Okay, So this will be the new position of B prime and C prime. Okay, we need to, this is based on the principle, okay, that these frames is going to sway, okay, according to this direction R prime. So let me write this out. Oops, prime first. Okay, the direction. So this B prime is not going to go to the left side. It will be going to the right side following the R prime. And the next principle is it must be perpendicular to your this member AB. Okay, if you can see that, if you draw this perpendicular projection of B, okay, you'll be meeting the B prime here. Of course, the deflection for the real case, it will not be so large. Okay, this is just in a as a grade form, okay, to make sure you know the direction of B prime. Okay, similarly for C prime, it must be going to the right, following this R prime direction, and it must be perpendicular. Okay, so the next thing, and another thing is A and D are not going to move anyway because there has been the restraint. Okay, so by the support. Okay, so next we can join, okay, draw a line, okay, through this new position of the joints, okay, to show our deflected shape. Okay, it will be seen like this. Okay, can you do it?
Yes. Yes.
Okay, so please raise your hand if you are not ready yet. Okay, so let us continue with this. Okay, so next we need to also know that the horizontal deflection, okay, or the deflection that dealing with this R prime, okay, must be the same, okay, for legs AB and also CD. Means that this deflection delta must be the same with this deflection delta. Okay, measured B to B prime horizontally and C to C prime horizontally. Be careful, if this sway may not always in horizontal. It may be diagonal, it may be in a vertical way. So depending on your R prime. Okay, but now this R prime is horizontal, so we are talking about this horizontal, must be the same. Okay, so please take note on that. Then we are going to determine the relationship, okay, for these deflections, because to determine the fixed end moment, we are going to use only one unknown, okay, one parameter in our calculation. Okay, we are not going to use many, so therefore we are going to use triangle, okay, to determine the relationship between these deflections. Okay, so we are going to draw triangle number 1, okay, and triangle number 2 for the other leg. Okay, can you do it now? Okay, so I will wait you to do this correctly. Okay, make sure this triangle, this diagonal line, okay, or hypotenuse of the triangle, okay, fit the BB prime, and triangle number 2 fit the CC prime. Okay. Okay, so once you have draw the triangles, you can draw it, in a larger way, okay, to write down the this how to say the deflection symbol. Okay, so as we have put in earlier, the horizontal, we use delta, okay, to define the dimensions of this horizontal, okay, horizontal dimensions of the triangle. Then we can use the delta prime for the vertical, okay, dimensions. And delta double prime for the hypotenuse. This is just, giving a names, okay, to these dimensions. Okay, so we address it number 1 is because it is triangle number 1. Okay, so I give you 2 minutes, okay, to draw for triangle number 2. Please combine them together with the delta here. Okay, can combine the triangle 1 and 2 in a big triangle. Okay, where they share this line. Okay, can you try that? 2 minutes later, I'm going to show you. Okay, the names, the symbols. Okay, this will be the, do you draw it correctly? This will be the other triangle. Okay, why we put this together is because they share the same dimension delta. Okay, so it will be better for us to put it together so that we can know the relationship. Okay, so if you can see that I also name these dimensions. I mean the point B prime, C prime, so that you know, okay, where is the location. Okay, so I have also put the number 2 here, but because this is a symmetry in terms of geometry, this delta 1 double prime is actually same with delta 2 double prime, and the delta 1 prime is actually same with the delta 2 prime. Okay, so let me know, raise your hand if you're not ready to move to the next slide. Okay, so I suppose you have get this right. Okay, so here, okay, so before we get to this, I would like to call a helpers here. Okay, how about Shazwani, are you here?
Yes, Doctor.
Okay, so Wani, I would like to ask, now what we are doing here is actually to define the deflection, okay, for each of the member, okay, and to determine the relationship between these deflections, okay. So I think the important thing now is to know what is the deflection for each of the member. Okay, so the deflection, there is a principle there. The deflection must be measured, it must be maximum, okay, and it must be perpendicular to the member itself. Like for example, AB, this dotted line is the deflection shapes of the AB, okay, meaning that all these are the deflections, okay, for member AB, but we are looking at the maximum and we are looking at the perpendicular, okay, to the member. Okay, can you tell in these symbols here, what is the deflection for member AB?
Delta along the delta B prime, B to B prime.
So it will be which delta here? B to B prime?
Yes.
It will be delta 1 double prime, right?
Yes.
Yes, you are right. So we are looking at this maximum, and it must be perpendicular to member AB, which will be addressing this delta 1 double prime. Okay, you are very right, Wani. And how about member CD?
Delta 2 prime.
Delta 2 prime, this one?
No, at the delta 2 double prime.
Yes, thank you very much. So we are looking at this CD now. So these are all the deflection value, but we are looking at the maximum, which is happening to C here, CC prime. Okay, and it must be perpendicular to the member. So if CC prime, we are referring to delta 2 double prime. Okay, how about BC, Wani?
Delta.
BC. Okay, we are talking about perpendicular to the member. Okay, if you look at the delta is this one, right?
Oh, delta prime 1 and delta prime 2.
Very good. Okay, because this B has deflected to B prime and C has deflected to C prime. So this is a new, alignment of BC. So when we are talking about maximum and perpendicular, and then we are talking about this line, right? So it will be delta 1 prime, and you need to plus because it is going up. Okay, the total is deflection is from B prime to C prime. Okay, measured perpendicularly, perpendicular to the BC. It will be delta 1 prime plus delta 2 prime. Thank you very much, Wani. So you may put in the notes here. So this will be delta 1 prime plus delta 2 prime. Okay, so let us have a break of about 5 minutes before we continue. Okay, so I would like to check your attendance. Okay, Akila, please take your attendance. Nurul, Aini, Nadira, are you here? Aini?
Yes.
Yeah, please take your attendance. Okay, I know Akila is here. So, and then, all right. Okay, so take a break. Okay, then we will continue. Okay, after 4 minutes. Okay. All right, are you back? Can we continue, class?
Yes,
Can
doctor.
doctor.
Yes.
Okay, so what we have done just now is just to get the deflection so that we can determine the fixed moment. Okay, so once we already know that deflection for AB, BC, CD, okay, their values, and we also know that here I have to highlight this. Okay, delta 1 prime equal to delta 2 prime is, we can just write it delta prime. Okay, why? Because the angle is the same. Okay, and the length is the same. Okay, so everything is symmetric here. So this triangle and 1 and 2 must have the same size. Okay, therefore we can just tell that this delta 1 prime is actually delta 2 prime. Delta 2 double prime is equal to delta 1 double prime. So this statement must be very clear. Then if you follow my lesson earlier, we need to write the fixed moment in terms of delta. Okay, so where is my equations? Wait. My equations is here. Okay, if you look at these equations, we are going to determine the fixed moment by using this equation, 6EI delta. That is why we want to get this delta. And we do not want to have so many symbols, okay, in all of our fixed moment. Only one, okay. So here I have a statement, okay, written here. I will going to represent all my fixed moment just using delta double prime. Okay, therefore I can say that I want to make assumption EI delta double prime here is equal to a value. It can be 10, 100, 1,000. Okay, so don't give it so small like 1 because you won't see the changes in your moment distribution. Okay, if you put it a bit larger, then you can see that the moments is decreasing, okay, significantly, so that you can stop, okay, your moment distribution table, okay, when you identify the changes. So, but we need to know the deflection, the relationship between this deflection, okay. So, for example, let us just write the fixed moment first, based on this equation. If you see that the equation is 6EI delta over L squared, we need to know the delta value, okay, and we need to know the direction. If you look at this appendix, okay, this moment, okay, is counterclockwise. Okay, why this is so? Okay, there is a principles for you to use, okay, or tips, okay. So to predict the directions, okay, we look at the displacement or deflection, okay, and our principle is to make sure it go back to the original position. So this is the deflected shape. Okay, this is the original position. So what we are going to do is we are going to push it back to the original position. That is why the moments will be in the counterclockwise direction. And these moments are going to act at the same direction, okay, for the other end. So if this is counterclockwise, at the other end also counterclockwise. Okay, let us try, okay, for our deflection here. So for, let's say for AB, okay, can you guess, class, what is the direction of the fixed moment? Clockwise or counterclockwise?
Counterclockwise.
Yeah, very good. So now we are going to push this back, right? Okay, so it will be counterclockwise. Similarly, it will happen to be the other end. Okay, so fixed moment AB, BA, it must be in the negative. Okay, if you can see that, negative 6EI delta over L squared. And the delta here for member AB is delta 1 double prime, right? So you have the delta double prime here, okay? And divided by the length of 5. Okay, so let us have a look on CD. Okay, class, How about CD? What is the direction of the fixed moment?
Counterclockwise.
Very good. So we push it back here. Okay, so similarly, it will be happening to the other ends. Okay, if you can see that, it will be having the same answer for as AB and BA. So if you look at that, we can put it as equal to CD, equal to DC, and it is also using a negative 6EI, and the deflection is using delta double prime at the second triangle. But they are having the same dimensions, so we can put it delta double prime as well. And the length is also 5 meters. So this is how you do it. So for fixed moment BC, how about fixed moment BC? Clockwise or counterclockwise?
Clockwise.
Yeah, very good. So this is to push it back in such, and this is to push it back here. Okay, so it will be in positive value 6EI, and you have a 2 double prime. Okay, we are adding this. Okay, over L squared. Okay, but right now we just want to have one parameter. We have chosen here. We want to represent all the fixed moment in delta double prime. So I want to know what is the relationship between delta double prime and delta prime. Okay, let us look at triangle one. Okay, delta double prime and delta prime. Class, can you tell me what is their relationship in terms of trigonometry principles?
Sin theta.
Cos theta.
Yes, you're right. So cos theta, you will know that it must be equal to delta prime divided by delta double prime, right? So this cos theta we can get from the dimensions. If you remember, the dimensions is 3 meter and the 4 meter, and we are talking about the theta here. Okay, if you look at this theta, it will be happening at this angle as well, theta. Okay, for this zigzag. Okay, then by this 90 degree here, so this will be 90 minus theta, and the theta will be here, acting here. Okay, so I need to make sure my theta placed correctly first. Okay, because I need to use the theta. So cos theta will be equal to delta prime divided by delta double prime. Okay, then the cos theta here is 3 over 5 or 0.6 based on this. Okay, cos theta is 3 over 5. Okay, so that is why you can see that they are actually substituting this delta prime with the delta double prime. Okay, so you can put it here 0.6 delta double prime and substitute these things into the equations. Okay, so I will give you a minute to study this, okay, before we go to the next. Okay, make sure you know how to get this value. Okay, because we already assume this EI delta double prime is 100. You can ask questions if you don't not clear. Okay, class, can you raise your hand if you are not ready to move to next slide? Anyone? Okay, so let's wait for another 1 or 2 minutes. Okay, class. So now I think what we have alien thing in your lesson has been over. So the remaining will be just what you have learned in your previous class. Okay, so if you look at this the PDF that I have shared with you, I have blank it. Okay, so please take yeah, 5 minutes. Okay, or probably longer. Okay, to 10 minutes. I will check your progress. Okay, from time to time. Okay, please complete this moment distribution table. Okay, we have placed the fixed moment due to the deflections here. Okay, and I would like to highlight on one thing, class. For the deflections, if your problems, okay, deal with support settlements, okay, so you need to, draw the deflected shape based on the settlement condition, and then there will be deflection in your potential members. I do not know, it depends on your structure. Okay, so once you identify which member have the deflection, you are going to get the fixed moment as what we have done just now. Okay, so now please continue with moment distribution method. Okay, for anyone would like to ask question, yeah, please, yeah, I'm still here. Okay, at the back of the screen. Okay.
Okay, Doctor.
Class, may I know what is the screen shown in your what can you see in your screen?
Stage 2,
Table.
moment distribution method.
All
Table.
right, all right, all right. Thank you, thank you. Okay. Can you raise your hand if you haven't complete the table? Okay. Okay. So we will wait for another 5 minutes. Huh? Okay, class, how about now?
Done, Doctor.
Done. Anyone?
Done.
Not yet? Okay, probably for those who are not, tidy up your calculation, you can wait later because I would like to continue to finish, the process. Okay, so I hope, oops, I hope you have obtained the value, okay, in this moment distribution table number 2. And at this stage, we name these moments M2 prime. Okay, so yeah, we couldn't have much time on determining the R prime. So I would like you to continue with doing this later. Okay, how to get this R prime 53.04. If you notice that just now the R is 30 kilonewton positive, which acting to the left, and now R prime is acting to the right. Right, 53.04. Okay, so you need to make sure that this R and the R prime must be acting oppositely. Okay, so if R is negative, okay, if the arrow is opposite,
Doctor,
yes,
we are still in the slide, the table tadi.
so let me check. So now I'm in this slide. Can you see determine R prime?
Yes.
Yes.
Okay, sorry for that. So now we need to know that how to get the R prime. The process, it will be the same with determining the R. Just to make sure that your R and R prime are acting oppositely. Okay, you can check through your value, positive or negative. Okay, so again, the process is you need to do the free body diagram. Okay, put in all the fixed end reactions. Okay, then the moments, okay, you can retrieve from this M2 prime right now. Okay, like for example, I will do one of it, negative 27.6 for AB, okay, which means counterclockwise. So you can place it here, counterclockwise, negative 26 yes, no, 27.6 is it? Sorry, forget. Yeah, 27.6. So it should be this one, 27.6. Okay, after you have put in all these moments and moments, okay, then you can start your strategy by determining the by. Okay, then ay, then you get your ax. Similarly, okay, your m's is to get the dx. Then you apply the summation fx equal to 0. Now the 30 kilonewton is not in this SWE analysis. So it will be r prime, ax, and dx only. Then you can get your r prime. Okay, so you need to do this, smoothly. Okay. So now this will be the last process where you need to determine the final moments. So these equations will be used. Okay, how to apply these equations? First, you need to know how to get the M1. M1 is from your moment distribution table number 1. Okay, M2 prime is moment distribution table number 2. Okay, and the R is from the stage 1 analysis. R prime is from the stage 2 number analysis. Okay, so now we also call this R divided by R prime as a correction factor. Okay, so let us just quickly try on this. So R divided by R prime, I will get this from the, okay. So R is 30 kilonewton, R prime is 53. Okay, so to make sure you know this, so it will be, can I write here? 50 divide, no, 30 divided by 50, oops, I forget, 53, okay? So 30 divided by 53, you will get the correction factor, okay, 0.6. Okay, then we are going to get for all the n moments, okay, so M1 we get from table number 1. okay, for AB. So this is table number 1. Okay, so 41.01. Okay, so we put it here, 41.01 plus, then we move to table number 2. Okay, it's 27.7. Okay, so we go to here, negative 27.7. Multiply with this correction factor, 0.57, let's say. Then you are able to get your final answer. Okay, so you proceed with all the remaining. Okay, so if you are asked to determine the support reactions, there is nothing about moment distributions method. You just need to use the equilibrium stat or equilibrium equations to solve for your other support reactions, internal forces. Okay, class, I think that's all from me today. I hope you can fill in, the empty of this tutorial sheet. Okay, so I see you next week. Okay, Wednesday. Okay, for those who want to ask questions, you may remain. Okay, class, thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank
Thank
you,
you, Doctor.
Doctor.
Thank you,
I have a
Doctor.
question.